Hello everybody and welcome to the last project of this course. In this project you will create a three-dimensional unit to segment liver and liver tumors in full-body CT scans. We will not work with single two-dimensional slices anymore. As usual, let's quickly discuss the medical background. Liver cancer was originally considered a more rare type of cancer. However, case numbers are continuously rising. Second to that, liver cancer is one of the cancers with the highest mortality rate. Therefore, as with the segmentation of lung cancer, this task is highly relevant. Note that the advantages of automatic liver cancer segmentation are identical to those of lung cancer segmentation. In fact, typically amongst all cancers. Please refer to the introduction of the Capstone project for more details. To tackle this task, we will use the dataset provided by the Medical Segmentation Decathlon Challenge, consisting of 131 full-body CTs of varying shape. As this dataset is quite large, we provide a resampled version where all axes were halved to reduce its size and to increase the training speed. As usual, please refer to the corresponding Jupyter Notebook for more information. Alright, let's have a look at a resampled scan with corresponding liver and liver tumor segmentation. As you can see, the liver is purple, whereas the lesions within the liver are segmented in yellow. Please note that in this dataset, the number of slices greatly varies. Some scans, such as this one, have only 40 axial slices, whereas other ones have over 200. So, now it's time to talk about three-dimensional data. As you might have already noticed, the problem with two-dimensional data is simply the lack of information. As an example regarding the last project, lung cancer is sometimes difficult to differentiate on a single slice. Depending on the position, the suspicious tissue might also be a large blood vessel or the top of the liver. However, if we increase the information flow to the network by, as an example, also feeding in neighboring slices, the network could learn to differentiate between those tissues. Therefore, let's expand our single slices into full volumes. Instead of handling a two-dimensional image of shape 256 squared, we now have a volume of shape 256 to the power of 3. This of course drastically increases the information content as the network now sees multiple slices or even all of them at once. By using three-dimensional convolutions, we can leverage this additional information. Unfortunately, as you might already imagine, this increase in information comes with a huge cost. Memory. A volume of shape 256 to the power of 3 needs 256 times more memory. Next to that, three-dimensional convolutions also increase the number of parameters of the model, as the kernel is now three-dimensional. As an example, in a two-dimensional convolution, a 3x3 kernel has 9 parameters. In a three-dimensional convolution, the 3x3x3 kernel has 27 parameters. The parameters are growing exponentially. However, the main problem arises when computing a parallelized forward pass or training the network. The just mentioned volume of size 256 times 3 needs only 64 megabytes in memory, but may take up to 20 or even 50 gigabytes during the forward pass. This is not possible on 99% of all computers. If you don't parallelize the forward pass, you may have sufficient memory, but inference is extremely slow. But of course, there is a solution. Instead of using the full volume, let's use smaller patches. We could split our original volume into 8 smaller subvolumes or patches, each having a shape of 128 to the power of 3. The number 8 comes from the fact that we can fit 2 of those patches along the x-axis, 2 along the y-axis, and also 2 along the z-axis, resulting in 2 to the power of 3, which is 8 patches. The following figure further visualizes that. The blue box is our original volume of shape 256 times 3. The black boxes within it are the smaller patches, each having a shape of 128 to the power of 3. You can see that we can fit 4 of those patches in the first row and again 4 of them in the second row. Parallelized prediction on those smaller patches only needs 2 to 3 GB instead of 10. This is the reason why, until now, you typically train and compute prediction on patches when dealing with 3-dimensional data. Of course, we want to obtain a final prediction of the full volume. Therefore, we need to aggregate the prediction based on the patches back together. The good question now is how to implement all that stuff. Luckily, there is an awesome library for that called Torch.io. According to the official documentation, Torch.io is a Python library for efficient data loading, pre-processing, augmentation, and patch-based sampling of 3-dimensional images in deep learning following the design of PyTorch. It provides huge functionality for all aspects of 3-dimensional imaging. Additionally, it directly comes with a beautiful augmentation library. Torch.io handles all images on a subject-based level. This means that each volume, as an example described by a Nifty file, becomes a Torch.io subject containing at least the scan and possibly the corresponding label. All operations are then performed on a subject-based level. The training flow is usually as follows. At first, we convert all Nifties or other files containing the volume to subjects and store those subjects in a list. Next, we create a Torch.io subjects dataset based on the previously defined subject list. If we want, we can pass an augmentation pipeline to this dataset. After that, we create a sampler to draw patches from the original volume. Torch.io provides multiple samplers. As an example, the uniform sampler, which simply draws patches at random, or a label sampler, which draws patches according to probabilities. You can use the label sampler to make sure that e.g. 50% of all patches contain a tumor or 30% of all patches contain the liver. The label sampler basically implements oversampling. This of course only works if a segmentation mask is available. After defining the sampler, we can create a Torch.io queue for efficient data loading. 3-dimensional data loading, pre-processing and especially augmentation is extremely computationally heavy. Therefore, Torch.io typically loads and processes the full volume and then samples multiple patches from it instead of a single one. Those patches are then stored in the queue. When training on a GPU, this process runs in parallel on the CPU. Last but not least, we create the PyTorch data loader based on a queue and proceed as usual by defining the model class. After training the model, we want to perform inference. When calculating a prediction with Torch.io, we at first define the grid sampler to split the subject into multiple patches. After that, we create a grid aggregator with the task of merging our predicted segmentations back together. Last but not least, we can compute prediction and perform aggregation. Alright, so much for the introduction to 3-dimensional imaging. Let's go back to the task of liver and liver tumor segmentation. We perform the following pre-processing steps directly with the help of Torch.io. No separate pre-processing notebook is needed. At first, we crop or pad all volumes to the same shape of 256 times 256 times 200. Cropping or padding simply means that we either pad the volume with zeros or crop exceeding slices. Next, we standardize all pixels into the -1, 1 range. Last but not least, we tell the dataset that it should use the first 105 subjects for training and the remaining ones for validation. The Torch.io subjects dataset needs to load a subject and return it with the corresponding segmentation. It directly augments scan and mask identically. We use small random scales and rotations for data augmentation. We don't use elastic deformations because of the computational overhead. After that, we use the label sampler to sample patches of size 96 to the power of 3. Hereby, 50% of all patch centers shall contain a tumor, 30% shall contain the liver, and 20% everything else. Last but not least, we create the Torch.io queue to sample 5 patches per volume per epoch. We then train our U-Net for 100 epochs using the Adam optimizer with an initial learning rate of 1e-4 and the binary cross-entropy loss function. Alright, now it's time to dive into the notebooks one more time and actually implement everything in practice. Thanks and happy learning!